Hello, today we will be discussing our topic of biomimetic actuation using shape memory alloys. Throughout this process, we were mentored with the help of our advisor, Dr. Castro. My name is Jeannie MacDonald.
I'm Alejandro Tovar.
And I'm Alex Verhoeven.
For this presentation, we will be going over our objective, design process, biomimetics, design overview, the heat treatment of nitinol, testing, analysis, results, solutions to problems we faced, as well as future improvements. For our objective, we designed an attachment of an exoskeleton overlay to mimic the movement of a hand utilizing nitinol as the prime material. We incorporated shape memory alloys to allow the shape of the actuator to retain its original shape after deformation. For our design process, we started by defining the problem and goals. We researched components for shape memory alloys. We then designed the electrical setup for the actuator, where we tested the load on nitinol. We tested the electrical connection on the assembled project and finished with assembling the components into the housing units.
Biomimetics is known as the study of biological systems and their replication as a synthetic model for the purpose of understanding said biological systems better. In our capstone project, the primary focus is the movement of the human hand, how the tendons and ligaments all move together when the hand opens and closes. The material that we are utilizing is nitinol. It is a shape memory alloy that is roughly 50-50 nickel and titanium. The shape memory characteristics of the nitinol is a solid-state phase change, where a molecular rearrangement occurs but stays in the solid state. After deformation of any kind, heat can be applied to return the wire back to its original shape, as shown in the image to the right. There is also a super-elastic version of nitinol, where the wire strand deforms to any force applied, but will then automatically recover its original shape without the need for heat application. This is a SOLIDWORKS representation of our final model, with nitinol running down the thumb and index finger, connected via housing rings on the distal phalanges of both fingers and the proximal phalanx of the index finger. We are using an Arduino Uno that sits in the Arduino housing on the forearm, with the breadboard connected to the outside of the Arduino housing. All wires coming out of the breadboard connecting to the nitinol are met at the knuckle connection. An external battery source powers the assembly and is connected where the power in and power out wires are.
Our 3D components were each designed through SOLIDWORKS. As seen on the left is our knuckle connection. The bottom smaller holes allow the nitinol to run through, while the top larger holes were used to run the lead wires through. On the right is our Arduino Uno housing assembly, which was used to hold the Arduino Uno with the breadboard attached on the back side and the power source on the side. The first housing ring, which is closest to the knuckle, is seen on the left, and the end housing ring, which is placed near the tip of the finger, is seen on the right. The sizing of the end housing ring is 10% smaller than the large first ring. The 3 small holes at the top for both designs are used to hold the nitinol in place. We only used 1 hole, but the other 2 holes are put in there in case we need to add more force or other degrees of freedom.
Heat treatment of the nitinol was difficult since we didn't have access to a furnace, so instead we had to use a stovetop burner. The first step was to anneal the wire by heating each section evenly over the stovetop flame for about 2 seconds until a dull red glow was achieved. Then the wire was quenched in ice water. Afterwards, the nitinol was set in its desired shape and held over a flame for 5 minutes, making sure all parts received equal heat treatment. The heat was measured at about 390 degrees Celsius, when in reality, the heat needs to be about 500 degrees Celsius. After the 5 minutes are over, the wire is quenched in ice water. To train the nitinol for two-way movement, the wire was dunked in boiling water and held for a few seconds to receive equal heat. Then the wire was straightened manually so that the wire remembers the position, and then placed in front of a fan for a few seconds. Repeat steps 6 and 7 about 20 to 50 times. And after about 10 times of this, you may stop straightening the wire manually when placing in front of the fan so the wire can return to its straightened position. There are a few observations noticed during the heat treatment of the nitinol. One being that after heat treatment, the wire never retained the true shape it was initially set in. It always slightly sprung back. Next is that the greater the temperature difference when training the nitinol, the more drastic the wire movement was. After heat treatment is complete, do not place back in the flame as it will tamper with the actuation when running a current through. Heat treatment of the 0.02 inch diameter wires made it too brittle and it would always snap when straightened. While on the 0.04 inch diameter wires, there would be no effect after heat treatment, most likely due to the fact that we did not reach adequate heat.
This is the circuit diagram used for our assembly. As you can see, there's the external source, which splits off into the two nitinol wires, and then it connects through two thermistors and resistors, which are used to measure the temperature as the nitinol heats up from the amperage that it's receiving. As you can see, there is no external input from the Arduino because the Arduino has a amperage limit of 4 milliamps, while our research and testing shows that we need something closer to 1 amp for the nitinol to actuate. This is the electrical hardware of our assembly. On the left, you can see where the housing fits and how the breadboard attaches to the Arduino housing. And you can see at the bottom that's where the external power source attaches to. On the bottom picture, you can see the thermistor and the resistor. They're attached in series, and there are two wires that lead back to the analog inputs of the Arduino. On the right, you can see the entire assembly of our hand. This is the electrical analysis testing that we did. So very simply, we just took the external power source, ran it through an ammeter, and then back to ground. We did this using to measure how much amperage we're getting from our power source. As you can see, there are lined. We assumed a straight line using Ohm's law. As the voltage increases, the amperage increases. And this testing was used to determine some theoretical versus experimental analysis.
In this video, two heat-treated nitinol wires were connected to a single battery source to measure their movement. The initial voltage was measured at 5.13 volts. As one can see, it takes the nitinol a few seconds to heat up from the current before actuation starts. Then it moves at a relatively steady pace until it reaches the end of its set shape, where the actuation begins to slow down drastically and eventually stop. They are currently still moving in their steady pace, and you'll see here in just a couple of seconds when they stop moving and start drastically slowing down.
This is our final testing of our hand. As you can see, the actuation is much slower, and our assumptions are because of part of the connections and the weight of the glove. Still has a good range of motion.
The initial voltage was measured at 5.35 volts. This final testing we did was with a hand in the glove. We found that the actuation was a much slower process with the hand inside the glove, since the hand naturally wanted to oppose the force of the actuation.
This is our weighted test pole. We measured 0.5 ounces of sugar. We experimented with different amounts, higher amounts, and we found that 0.5 ounce was our limit. Part of this was due to our inability to have proper heat treatment of the wire that prevented us from pulling a much higher weight.
From the videos taken during testing, distance traveled by the nitinol wires was found, as well as the time. There were 3 points taken, and at each point with these values found, velocity was calculated. As you can see in the table below, the point 1 had the highest velocity of all of them. After velocity was found, we used kinematic equations to determine the acceleration of the actuation. And then from the weight pulling test, the mass of the sugar was determined and used along with the acceleration previously found to determine the force, which, as can be seen, are relatively small values.
As far as our results, only actuation of one finger was achieved in the final assembly. All of the hardware was troubleshooted and replaced, but we could not get the second finger to actuate. Since the nitinol wasn't properly heated, only half an ounce of sugar would be able to be lifted, when in reality, it can pull much higher amounts than that.
For a few solutions to problems we faced, we found that the heat treatment process of the nitinol kept giving us problems. So we attempted several different methods and tested each size of nitinol for comparison until the actuation began working properly, as stated in a previous slide. We noticed the alligator clips were vibrating too much on the surface during the preliminary testing. So we wrapped the end of the clips in UHMW tape to prevent friction on the surface while the wires would move during testing. We also found that the wires would start to smoke if tested for long periods of time and used too frequently. So we added a heat-resistant spacer utilizing heat shrink tubing to wrap the wire. If we had more time to continue working on our progress, we each agreed to configure this circuit, which would allow for greater amperage in the system without fear of burning electronics and melting parts. We would also gain access to a portable power bank that would allow for greater amperage, and we would utilize thicker lead wires.
For future improvements, we can add a load cell, and it can be used in our system to measure the pressure so that we could potentially pick up things. Also, we can use some sort of pulse modulator that would allow for more even heating of the wire. Currently, we were using a DC source, and the positive side that was connected to the wire would get a lot hotter than the end of the wire. So using more even heating would allow for a more even, greater actuation of the wire. Having access to a furnace would also help us fine-tune our nitinol treatment. We can get the nitinol to work within a better temperature range and potentially at a lower amperage. Also, we would like to enable the actuation to the entire hand rather than just 2 fingers, and also create a housing unit for all the electrical components. We would like to thank David for assisting us with our 3D printed materials, and Professor Castro for assisting us during the entire process. Thank you. Have a wonderful day.